I'd like to welcome you all to our conversation with the Parkinson's Foundation today, presented by Jan Hatherell, Director of Operations. I'm going to go ahead and start to read our disclaimer. So the WildTech DC Senior iPad program, its owners and presenters offer technical assistance, virtual health, well-being information designed for educational purposes only. You should not rely on the information and any applications or topics made by WildTech, including but not limited to mobile device applications and any social media pages maintained by WildTech, its owners or presenters as a substitute for professional medical advice, diagnosis, treatment, or legal advice. Thank you so much for letting us read the disclaimer. Make sure all TVs and cell phones are silenced to the best of our ability so that we can give others, and most importantly ourselves, the most immersive experience. And I recommend you have a pen and paper and a notepad so you can write some things down in case you need to view them later. Again, thank you so much for letting me read the disclaimer. And again, today we have the Parkinson's Foundation. So Jan, if you could introduce yourself and what you'll be covering today, we would appreciate that. And again, thank you so much for coming on to our sessions again.
Okay, hopefully I'm trying to share my screen. Has that happened? Not quite yet. Ah, there you go. So you don't get to see me, which is probably much better for everybody. Okay, so let me introduce myself again. So I'm Jan Hatherell, and as you can tell, I originally am British. Okay, although I am now an American citizen, which has changed since I last spoke to you all. Okay. My big thing at the moment that I'm dealing with is the PFNCA symposium. So we do one annually, and it's our medical advisory board that run it. So it's done properly by doctors. And the lecture I'm going to show you is one of the ones that was shown in a previous symposium, so you can get a good flavor of what the symposium might be about. Okay. This year, they're doing it differently to how it was normally, and it is going to be live online via Zoom. So just what you're used to, because you're used to using your iPads for things. And it's about 10 a.m. to 3 p.m. on Saturday, May the 18th. You don't have to watch all the way through on that day if you don't want to. But then there will be view-on-demand sessions of 18 new lectures that have been recorded by our medical advisory board members and also by some of their friends and colleagues. Okay, so we have them in 5 themes. We have them in mobility aspects of Parkinson's, autonomic aspects, cognitive aspects, what is current on the research for Parkinson's disease at the moment, and there is an awful lot of that at the moment. I can't read a science book at the moment without seeing that there is some new aspects that they're investigating that might actually be hopefully bringing some fruit for people, some more treatments, some more understanding of the causes of the disease, which is really interesting. Okay, and then the final one is navigating the healthcare team that you will need if you are diagnosed with Parkinson's. And I know perhaps many of you aren't people that have Parkinson's, some of you may, but you may also have some friends and relations that might be, or you might think they have. And this is always very interesting for you if you are in that circumstance. So if you do want to sign up for this, and here are our speakers for this year, okay, all of our medical advisory board members and their friends and colleagues. Okay, then you are, and it's normally $60, but because of our relationship that we have with you at WildTech, we are absolutely happy to offer you to have that access for free. Is that okay with that? Everybody happy? Any questions about this year's symposium? So the lectures are available. I think it's just say there right until the end of August. So you can Zoom and watch any of the 18 lectures from May the 19th to the end of August if you are interested. Questions about the symposium?
Thank you so much for that, Jan. I really appreciate that. So if someone was interested in attending, what would you need from them or us?
I need them to contact me. So you can either go to our website, here it is, the Parkinson Foundation of the National Capital Area, which you can easily Google and get to. And then if you send an email, there's an email address down here, pfnca@parkinsonfoundation.org. Okay, it's probably the easiest way to do it. It's on all of our, or you can just email me directly, jhatherell@parkinsonfoundation.org. Okay. And if you do that and say that you are, a member of this group that meets, then I'd be absolutely happy to offer you a scholarship. There are lots of people saying things in chat. Are you monitoring that?
Yeah, that's myself, Jan. So I put the both emails, so the
Okay.
PFNC email and your email. So if you are interested in attending this session, this symposium, please email Jan or PFNCA saying that you're part of the Wild Tech program and would like to attend. Is that right?
Absolutely, yeah. And I will send you the code for not having to pay, which is useful.
Yes. So please check out the chat, everyone. Again, the first link is their actual website you see Jan presenting. The other two are the emails you can contact either, again, PFNCA or Jan directly as well.
Okay, fantastic. Right, well, with no further ado then, let's get on to Dr. Von Köln presenting to you. I need to get
Yeah,
you.
so even where it says CC under the video, you might be able to get some captions going on.
Where does it say that?
Right.
Oh, there.
Mm-hmm.
Okay.
Yep, so hit
Let's
English.
try. Okay. All right. I might help because
Yeah,
okay. Yeah, it's jumbled it a bit, but that looks okay. All right, can we go to full screen?
sure.
Okay.
And then if you want to get rid of the transcript, so maybe the screen will be bigger, you could keep it up, whatever you
I think
prefer.
that's probably best to have that, then people can read it if they
Yeah,
isn't
that as
it?
well. So okay, it's okay. I'm glad that we were able to figure that out.
Should we get rid of have you got all
Just
three?
let's see how the captions look because it might be redundant a little bit. So if
Okay,
we
let's see how we go. Can you control it as well as me?
no, just yourself, Jan. So if you hit play, we'll be able to see it.
Okay, let's see how
Hi,
it goes.
welcome
Oh,
to my presentation
Yeah,
on
so
genetics of Parkinson's disease. My name is Rainer von Cullen. I'm an assistant professor at the University of Maryland School of Medicine in the Department of Neurology there. And as the title of the talk promises, we will talk about genetics of Parkinson's today. I received funding from the NIA and from the University of Maryland Strategic Partnership Empowering the State, but otherwise I have no conflict of interest. This talk will...
So I'm just going to say, does everyone know what the NIA is? National Institutes?
Be divided into three parts. I will give a brief overview of genetics, as genetics is obviously a complicated topic, and don't worry, it will be manageable and hopefully not get lost in too many details. And then the second part will be dedicated to the question, is Parkinson's disease a genetic disease? And part three will address the question, should you undergo genetic testing or not? So we will start with a brief overview of what genetics actually means. And some of it may sound familiar from back in school, but you will see it's not too bad, I promise. All right, so by definition, genetics is the scientific study of how certain qualities or traits are passed down from one generation to the next, or from parents to offspring. You probably all remember this guy, or maybe not. So this is Gregor Mendel, who discovered some of the fundamental principles of genetics when he did his famous experiments with peas, so pea plants. And he's the one who coined the terms dominant or recessive traits, which we still use today to describe the parents of an inherited disease within a family. In some ways, he is really the founding father of what we consider genetics today. So again, those terms are just pretty much unavoidable when we talk about genetics. So I do want to mention them and explain them real quick. Dominant means that a trait goes from generation to generation. So if you, for example, had, we're talking to this person here, square is always a male, circles are females. And so this is somebody with a certain disease, let's say Parkinson's disease, and that's what the black color means. And those family members, this is obviously a family tree, and the family members who are shown as white symbols do not have the disease, and the black symbols, those people have the disease. And so this is a person who is affected himself, and his sister is affected, as is his dad, and also the dad's mom, or the paternal grandmother, is affected here. And then there's an uncle and a cousin. So that shows you a typical dominant inheritance pattern here, where every generation is affected by this condition. In contrast to that, in a recessive disease, you see that in one generation, there are several family members that are affected. So, for example, if you talk to this person here, then who does not have the disease, you will find out when you talk to that person that the mother had the disease or has the disease, and also the mother's brother or the uncle of this person, but nobody else in the following generation or in the previous generation. However, and we'll get to that in a minute, what that really means, there will be carriers. So in a recessive pattern, both parents of the people that are affected have to be carriers of a certain trait, but that alone does not give them the disease. But then when these two carriers together have children, then a certain percentage of the offspring will have the disease. But then in the next generation, it will be back down to the carrier status only. So this person will not have any risk of having the disease unless that here also is a carrier, which in our example is not. So anyway, so it's just really about the pattern without getting lost in the details, like I promised. Dominant is really a vertical here from generation to generation kind of pattern, and recessive is more of a horizontal within one generation pattern, and not above and below that generation. All right. Now, a few more other key terms that we need to use when we talk about genetics and everything that has to do with it. The information for a single trait that gets passed on from one generation to the next is really what we call a gene. And today, unlike Friar Mendel, I guess, we know that genetic material is contained in the DNA in each cell in our body. So here you have a little picture of a schematic of what DNA looks like, this double helix of these two strands intertwined. You may remember that from school or from other reading that you have done in the past. And DNA is translated into proteins, which are the building blocks of our bodies. So in the DNA, that is contained all the information for all the proteins that are used to build a human body, basically, and how they function. And this is a principle that the DNA is transcribed into intermediate product called a messenger RNA. You don't have to remember that. And then the whole thing is translated into proteins. So one gene is then the segment of this DNA that contains the code for one specific protein. And we carry two copies of each such gene in each cell of our body, one copy from mom and one copy from dad. So two copies for each gene. And genetic variants in DNA tend to pop up randomly over time and may affect the quantity or the function of the proteins, or often these variants really don't make any have any impact on the function or the quantity at all, and they're just variants. But sometimes they do affect either the quantity of the function of the protein. And so this is just a schematic to illustrate what that looks like. So here you have a gene, which is a certain part of the DNA, has all the information for one protein, and so we call that a gene. And there's all these base pairs here that contain the genetic information. That's really what the DNA is made of. And if there is, through some mechanisms that would go beyond the scope of this talk, there can be chemical changes ultimately, and then you have a little variant introduced here. in this gene, and that can have an effect on the protein that is coded by this gene. And if it actually causes disease, if this variant causes disease, then we call it a mutation. So a mutation is a DNA variant in one gene that causes disease. And in general, those genetic variants or mutations are passed on to the next generation. And coming back one more time to these two terms, dominant and recessive, with the knowledge that we have now recapitulated, the whole thing and the statistics of it make more sense. So you have one gene here, and most people have two healthy copies. In this case here, this man has two healthy copies, one from his mother and one from his father. But his partner or wife here has one diseased copy of the gene, or a gene copy with a mutation in it, and one healthy one. And that is enough. The one bad copy is enough to give this woman the disease. So that's why she's depicted in this blue color here. Just like in these pedigrees, you know, a certain symbol just symbolizes having the disease or not. And then if these two people have children together, 50% of their children will get this diseased copy of the gene, or the mutated copy of the gene, from the woman. And so 50% of them will have this copy and will hence also have the disease, and the other 50% will not. So this is how a so-called autosomal dominant inheritance works. And then in recessive, you have the situation that both of the parents have the one copy of the mutated gene, but that alone is not enough to cause the disease. So that's why both parents are carriers but healthy. And then 1/4 or 25% of their children will, just by a random statistics, by a random distribution, will get the copy with a mutation from both parents, and this child will then, or this person will develop the disease, and 50% of them will be carriers, and 25% will not get either copy with a mutation. This child here got both of the healthy copies and will be healthy and will not be a carrier. Anyway, so that will then hopefully illustrate how that works with the recessive and the dominant inheritance. And those are the two classic patterns of Mendelian inheritance. Okay, so with this, equipped with...
Let me just pause there. Is there anybody that has any questions that they want to ask about this first section?
Thank you so much for that informative video, Jan. I felt like I was back in bio class.
Yeah, exactly.
With the P plan. So that's really interesting. So we don't have any hands. Again, if you have a hand or a question about what was just showcased, please raise your hand. But Miss Maddie in the chat, she said something like sickle cell when they were talking about the autosomal recessive and dominant gene. So sickle cell, I know, is a recessive disease.
And
so
I always think that the way it's presented, you know, and it's percentage chance, you know, so if you have one child, all right, it's probably the best way to think of it, rather than showing, like he showed 4 different ways of arranging the genes, which is, you know, okay and sensible. But the whole point is that each time you have a child, if you have the 2 recessive carrier parents, all right, each time there is a 25% chance that the person who is going to be their child could have the disease by inheriting both of them. So just because you have, if you said had 4 children and with 2 carrier parents, doesn't mean to say you're definitely going to get one that's got the disease, 2 carriers, and one that hasn't. Because each time, you know, the egg is made, fertilized, and goes on to produce a baby, there is a 25% chance that it will be somebody that has the disease, 25% chance that it's somebody who doesn't have the disease at all, or they could produce 50% chance of having one copy of the defective gene and be a carrier. Okay, so it doesn't mean that you're definitely going to have somebody that's got the disease if you've got two recessive parents with a recessive disease like sickle cell. Okay, does that make it any easier to understand?
Thank you for that, Jan. So if someone does not get the disease, if the child does not have the disease, so they're not a carrier anymore, or are they still a carrier if they don't have the disease?
No, I'm just, can I go back to his picture without playing anything? There and still keep it paused. Okay, so can you see the picture on the screen? So this person,
Yes.
all right, they have a copy of a healthy gene from dad, shown here, and they have the diseased gene shown here, all right, from mom, which means they don't have the disease because it's recessive, like sickle cell. Okay, but this person will be a carrier of this condition.
So there's a 50% chance for that. There's a 25%
Exactly. So
chance for the other situations.
Yeah, the other way, what this person here is showing that they have presumably the other way round. They'll have the carrier parent would be from dad and the other one from mom. All right, and that person will also be a carrier of the unhealthy gene that causes a disease. This person, by chance, has that one and that one, neither of which are infected or unhealthy, and so this person is completely unaffected despite having two parents who are carrying the gene. So in the case of, you say, sickle cell, it's quite possible that two people carrying sickle cell, all right, will have healthy children who are not affected at all, about a 25% chance as each child is born. Not exactly to get the pattern shown there, 4 children, one of each, as it were. Okay, does that make sense?
Yes, I think that's just a great thing to point out. And for dominant, it's like a 50-50 chance, basically.
Absolutely. If you get that one from mom, all right, either way, you are going to have the disease, is the whole point. Okay. Got it?
Well,
Okay.
thank you. That's so informational.
If you've got a dominant illness as a person, all right, and you've been told by the medical profession that your illness is a dominant one, you have to think very carefully about whether you want to have your own biological children in a straightforward manner. It might be that it might be best for you to say have IVF, for example, and have the resulting embryos screened to see if they have the healthy version of your gene. And then you would have an unaffected child. Does that make sense? I think a lot of people who are carrying a dominant illness would be doing screened IVF in order to make sure that their young people that they're giving birth to do not have this disease that they have.
Thank you. Maddie also said oh, go ahead.
Carry on.
Oh, Maddie also said these are some of the reasons why they used to require blood tests before marriage years ago. Is that true?
Absolutely. Yeah, especially in populations that were prone to sickle cell. Absolutely. Wow. Because you didn't know, you couldn't at that stage screen, you could in the recessive case also screen for the embryos to try and make sure you have the unaffected child if you know that you also already are a carrier for sickle cell. Then you could screen for embryos and make sure you have an unaffected child, which would be marvelous for you, because sickle cell can be a very debilitating and painful disease. But there are lots of other genetic diseases. It's not just sickle cell. That's a very good example, though, of one that you're talking about. Okay, is that helpful to folks? Okay, shall we go try and find back to where we were with where were we? He was just about to start the second section. Right, let's go there. I've lost it again. There you go. Whoa, fingers a bit wobbly here. Oh, come on. It doesn't want to carry on from there for me. Just, oh, never mind. That's fine.
Yeah, I think you're good to go to play.
Yes, dominant inheritance related to that Parkinson's disease, a genetic disease or not? or related to that, does Parkinson's disease run in families? So first of all, Parkinson's disease is fairly common. There's almost 1 million people in North America alone that have Parkinson's, and an estimated 10 million people worldwide. So it's obviously not a very rare disease. And even, it's obviously age dependent. So 1% of the population over 60 years of age is affected by this disease. So it is fairly common. So you would think if it really strictly runs in families, we would have known that for a long time. So, and it is pretty much clear from studying this disease over many years since it was first described, even centuries at this point, that there is usually no Mendelian pattern of inheritance, or in other words, families with such a Mendelian pattern of inheritance, either dominant or recessive, are exceedingly rare. So therefore, the traditional conclusion in all the old textbooks, etc., was that Parkinson's disease is not an inherited disease, or it's not a genetic disease. And genetic factors do not seem to play an important role in the pathogenesis of PD, or pathogenesis is one of these fancy medical terms just to say that in the way that Parkinson's disease develops. So that, again, this is not the conclusion of my talk. This is what people used to say based on the fact that they just almost never saw a family with such a classic dominant or recessive pattern of inheritance. However, people then, when they looked at the whole thing more in detail, they found that if somebody has a first-degree relative, so either a sibling or a parent with Parkinson's, the risk of that person to develop PD is more than double compared to the general population. So what it actually is for the general population, there's roughly a 1% risk to develop Parkinson's disease. And if you have a first-degree relative, you have a 2% risk. It's obviously not 50% or something like that, but it is double. So that actually argues very much in favor of some genetic component. Interestingly, the risk is not increased for relatives of late onset PD. So somewhere in the age range of mid-60s or so, if that's when you develop Parkinson's disease, then your first-degree relatives will actually not have an increased risk. So this statement up here is mostly relevant for people with somewhat younger onset Parkinson's disease. And people look in twins, and then those studies were inconclusive. Twin studies are a popular tool of genetic research if somebody wants to even figure out, is a disease genetic at all or not. People often try to look in twins, and for obvious reasons, and that was actually inconclusive. Some results seem to suggest that there is a genetic component. Other results seem to argue against it. So that really did not solve the mystery. And then in the late 90s, that was really a big breakthrough year for PD genetics, and because of a couple of major scientific findings or breakthroughs. So first of all, there was that publication in the journal Science in 1997, where they described mutations in the alpha-synuclein gene as a cause of a familial form of Parkinson's disease. And here you see the reference from Science magazine in 1997. And what they had studied is this large Italian-Greek family with a clear autosomal dominant pattern of Parkinson's disease. And that family was or is a really large family, and so that gave them the opportunity to identify the genetic mutation and the affected gene that is responsible in this particular family for this disease. And that's what they published in this paper. And that was the first time that a mutation in one specific gene was identified to cause Parkinson's disease. So this is really like the Big Bang moment for genetics in Parkinson's. So, however, it became clear very quickly that this is again, an exceedingly rare form of hereditary PD with this autosomal dominant inheritance. So this was really fascinating and enlightening in many ways. But when people then looked, all across the world, really, how many families are there with this mutation, they kind of were disappointed because it turned out to be very, very rare and didn't really explain most families or most forms of Parkinson's at all. However, the second part of this big breakthrough year followed suit very quickly, and this was another major publication this time in the journal Nature, where another group found that alpha-synuclein, the same gene that is mutated in this family that I just mentioned, is actually the major component of these mysterious Lewy bodies, these protein inclusions that form in Parkinson's disease in general, in pretty much everybody who has the disease. And if you look at the brain under the microscope, you see these inclusion bodies, these little dense bodies that are abnormal. And people had always wondered what is in them, what's the building block of those. And so this group found that the building block of these Lewy bodies is actually alpha-synuclein, not only in those very, very few patients who have this mutation, but rather in pretty much everybody in the normal, so-called normal or non-genetic form of Parkinson's disease. Those Lewy bodies consist of alpha-synuclein, the same protein that is, when the gene of this protein is mutated, causes a dominant form of Parkinson's disease. So this cross-linking of the very rare genetic form of Parkinson's and the conclusions and what we learned from that for the much more common non-genetic form of Parkinson's, that was really the big thing back in '97, and the implications really reverberate until today. Another important finding that was published a year later, also in the journal Nature in '98, was a recessive form of Parkinsonism, as I call it here. So it has a few aspects that are not quite typical of Parkinson's disease. So they're called a juvenile Parkinsonism, so really early or young onset, but very similar to Parkinson's disease. And this is the recessive form. So they they named the gene the Parkin gene. So this was this is from the original publication, a typical pedigree here with a typical pattern of recessive inheritance. And the disease is described as autosomal recessive juvenile Parkinsonism. You don't have to remember the details here, but just to say, many things are typical, good response to levodopa, slow disease progression, but then there's quite a few atypical features too. Very early onset, usually before the age of 40, which thank goodness is obviously not very common in Parkinson's in general. An early foot dystonia or cramping of the foot, early onset of levodopa-induced dyskinesia, which are these fidgety movements that some people get when they take levodopa at a higher dose or for a long time. So there were some features that were unusual, but overall it is still clearly recognizable as something very, very similar to Parkinson's disease. The most important thing is really that they had that very early onset, and when people then looked a little bit later, they noticed that these patients do not have Lewy bodies. So they don't seem to accumulate alpha-synuclein, but that's just a little side note here. We will not talk about the implications of that observation during today's talk. Just wanted to also mention that the name Parkin always caused some I guess either consternation or amusement in our co-workers and friends from the UK, because in the UK there's that Parkin gingerbread that has been around for a long time, and they always felt that the gene should have gotten a different name, but I guess we still call it Parkin, and yes, so it's just one of these little anecdotes that makes the whole thing a little more entertaining, I guess. Anyway, so Parkin gingerbread has nothing to do with the Parkin gene. All right. So these are two classic examples of what we call monogenetic forms of Parkinson's disease. So What is that term now again? If a mutation in one gene causes PD and the pattern of inheritance follows one of the classic Mendelian patterns, dominant or recessive, then we call it a monogenetic or monogenic form of PD. At this point, we know 12 plus minus monogenic or monogenetic forms of PD. And the two that I have discussed so far are actually very rare, or in other words, the mutations in these genes for alpha-synuclein and Parkin, and really most other monogenetic forms of PD are actually very rare. Nevertheless, studying the effects of these mutations has taught us a lot about the mechanisms of Parkinson's disease in general. So I think the example of alpha-synuclein forming Lewy bodies is a perfect example of that. That even if these genetic diseases are super rare, that's not why most people have Parkinson's. It's still really important for us to understand the disease better, to study these things. So this is just to give you the overview. Don't worry about the details, obviously. This is just a list of the genes that have been identified so far. The labeling goes from PARK1 all the way up to PARK23, but some numbers were later deleted. So it's really a list of plus minus 12 or so genes that seem to really cause monogenic Parkinson disease. And among them is the synuclein gene here that I talked about earlier, and the Parkin gene. Those were the earliest ones. And in the meantime, we've found quite a few more. And there's one more that I will talk about in a minute. But all of them overall are quite rare. So I want to come back to an idea that I introduced earlier, though, that there's not only mutations in DNA, but in general, there's DNA variants that pop up from time to time in different parts of our genes. And that's something that is really important for the next part of my talk, which is that these common genetic variants can also be of relevance for the risk to develop Parkinson's disease. So simple genetic variants, not mutations, but just variants of a single base pair in the DNA are quite common in the human genome, which is the entirety of our genes, right? And such variants are called single nucleotide polymorphisms, or SNPs. You don't have to remember that. Just in case you have heard the term before, I wanted to mention it. So that's these very simple single piece kind of DNA variants are called SNPs, depending on where and what you read about them. So some of these variants, or SNPs, have an influence on how likely it is for the person with that variant to develop Parkinson's disease. However, the risk to develop the disease in a carrier of such a variant is typically only very slightly increased. For example, if the average person without such a variant has a risk of 1% to develop PD, then the carrier of such a PD risk variant has a 1.2% to develop the disease in their lifetime. In other words, it's a very small increase, 20% increase, if you will, but so, you know, it's really not going to be very noticeable. It's not like in that family, all of a sudden, there's going to be lots and lots of people with PD. So this is really something that can only be found with in a large sample or in a large group of patients and what we call control people who don't have the disease. And then you do complicated statistics, and that's how you find that kind of thing. But it is definitely a finding that has been confirmed over and over again. And actually, back in 2014, we already had 28 of such so-called risk variants of Parkinson's disease. This is just an illustration, you know, how complicated it gets and how long the list is. Actually, the list at this point is more than 3 times as long. At this point, we have 90 and still counting, basically 90 such variants that have been associated or have been identified to be associated with a small increase or decrease of risk of Parkinson's disease. And those things probably add up to, and so it gets pretty complicated. But the key thing here is that these are common variants, unlike these mutations we talked about earlier. These are fairly common variants, but their effect size is very, very small. Altogether, however, they explain roughly 30% of what is described as the heritability of Parkinson disease. So, so we understand better than we used to why there can be more first-degree relatives, for example, with who both have the disease, even if there is not one genetic mutation that we can identify. So that may be due to these factors here that have a small effect, but nevertheless do have an effect. And then I want to get back to this table one more time. Remember, this is the list of all the monogenic forms or monogenic forms of Parkinson's, and we had talked about synuclein and Parkin. There's one other important gene here that I want to talk about for just a few minutes, and that is the LRRK2 gene. And what is special about that is that it is a little bit between the mutation and the common variant situation that I've talked about on the previous slide. So LRRK2 is another example of a dominantly inherited form of the disease, autosomal dominant inheritance. It has pretty much a typical, what we call phenotype, or typical presentation of Parkinson's disease in the affected patients. So if you have somebody with such a mutation and the disease is caused by that, you wouldn't necessarily notice that there's anything special compared to all the other patients that somebody like me sees in their patient every day, in their clinic every day. It is not super common, but also not super rare. It is found in a mutation in LRRK2 is found in 2% of the non-familial cases of Parkinson's disease in the US, for example. The numbers are a little variable, but it's somewhere in that range. And depending on the ethnic group of a patient, it can be actually much higher. So Ashkenazi Jews or Arabs of North African descent have a much higher percentage, or have a much higher chance of having a mutation in this gene. And if you look at patients who have a first-degree relative and have PD themselves, then there's actually a 40% chance that they have a mutation in LRRK2. So in these ethnic groups, LRRK2 mutations are actually quite common, especially if you find that there's a family with several affected family members affected by PD. Interestingly, not everybody who has a mutation gets the disease. And that's what the point I want to emphasize the most here. So it is age dependent. So at age 60, only 30% of patients or of people, of carriers of a LRRK2 mutation will actually develop Parkinson's disease, motor signs or other signs of Parkinson's disease. At age 70, it's 50%. At age 80, it's 75%. So these numbers are rounded a little bit, by the way, but just to make it easier to remember or to grasp. So even at age 80, only 75% of the affected people affected by the mutation will actually be affected by the disease. Or to flip it around, 25% with a disease mutation do not develop the disease. So we call that incomplete penetrance. And it really means that it is actually more of a risk factor than a real disease-causing mutation, right? So it's really something in between, a classic mutation that pretty much always causes the disease, and a risk factor which only increases the risk by just a little bit. So a LRRK2 mutation is really something in between. It often, but not always, causes the disease. So this has really made the situation very, very interesting, but also really complicated with the genetics of Parkinson's, that there is these different scenarios depending on what type of genetic variant we deal with. So coming back to the original question here for this part of my talk, does Parkinson's disease run in families? I would say yes, but only in very few families due to exceedingly rare mutations does it really strictly run in families in the way that Mendel would have recognized it as, one of the typical patterns of inheritance. What really runs in the family is the risk for Parkinson's disease for the most part. And there's really three types of genetic factors that we learned about in the last 20 minutes. There are the common variants that are quite common in the general population, but each of these variants only has a very small effect on the risk of PD. There are rare mutations that are often, but not always, associated with the disease, or they do not always cause the disease. And then there are these very rare mutations in specific genes that pretty much always cause the disease, in specific genes that always cause the disease from generation to generation. So those are the different aspects of genetics in the PD field at this point.
Okay. I see Louise has raised her hand. Is there a question there?
Hi, Jan. Again, thank you so much for the video. I definitely learned a lot about genetics and Parkinson's. Before we hear from Louise, Ms. Dina put a question in the chat. I'm not sure if it has to do with the sickle cell conversation from before or Parkinson's, but she said, what if tests prove the unborn child is infected? And with Roe versus Wade and things of that nature, what would the doctor typically suggest if that were the case?
In my experience, I mean, obviously, I'm much more au fait with the British situation than I am with the American, but I don't think doctors usually recommend anything. They would usually give the results of the, I mean, one of the things that we know that people might screen for is Down syndrome, which is particularly common in the babies of older mothers. But usually because there's been some kind of genetic mutation, in the mother's egg cells during her lifetime. And then they screen for that. They don't, say you should have an abortion. They say, you need to know, you've had the tests done. You need to know that it is a positive or it is a negative test. If it's a positive test, then the mother and father to be might ask questions about, what would that mean? How would it be? Blah, 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 but there's no suggestion that it's automatically that child would be aborted. I mean, there are obviously much more serious conditions which can be tested for and found out about unborn children where, the abortion is much more likely to be something that will be discussed because the likelihood of the child living beyond hours after birth or even dying in utero are so very great because the damage is so enormous. But there's I don't think medical professionals recommend abortion. They offer it as an option, knowing the circumstances, having had the testing done in utero. Does that make sense?
Thank you. Yes, thank you so much for your answer, Jan. I really appreciate that.
Does that answer Louise's question, or whoever it was his question?
Dina, please share in the chat, if that helped out. While you do that, Louise, you had a question for Jan about the video that we've watched?
I got part of my answer from what the question before was about family members, if they recommend any testing. And I wanted to ask about if there's anything else like exposure to chemicals or something like that that can also cause
Parkinson's. Yeah, yes. Absolutely. There are absolute connections for some people's Parkinson's disease with exposure to chemicals. The one that is obviously very current is that people who have been exposed to Roundup, the weed killer, in great quantities, that there is a fund to pay out to them in the US. I know there's been a court case and a fund set up to pay out to people who had large exposure and who have Parkinson's. And obviously the current one, which is advertised on the television all the time, is the people who were exposed to the relative poisons. I don't know what exactly the poisons were at Camp Lejeune, the
For
Marine.
you, Rebecca.
All right, and
Mhm.
Parkinson's is an outcome for a lot of those, and so they also have a court case going, I think, where they've been told from Congress that there is going to be a payout of funds because they should not have been exposed to those chemicals. So, I mean, absolutely environmental causes. I mean, I was interested in the juvenile Parkinsonism one, because obviously we know, one of the most famous people who has Parkinson's is Michael J. Fox, and he had it from a very young age. And the interesting thing is, as you saw, the chances are so, small, like 1% of the population to have, or less, to have Parkinson's at any particular moment, especially young onset is very much rarer. And yet there were several people who worked with Michael J. Fox on the set of the TV program that he did before all the movies. I don't know what it was because I've never seen it, but there was a TV series that he did when he was really quite young. And several people, I understand, from that set of people, people working on the set, have all developed Parkinson's. And they do wonder if there was an environmental effect there, but don't think it's actually ever been proven. But there are certainly environmental things which can increase the risk for certain people. I come back to my husband. I don't know if I told you before that my husband has Parkinson's and his grandfather has Parkinson's. So there's some kind of familial link, but it's not first degree relative that Dr. Von Kloon's been talking about. But the other thing is that his grandfather was a farmer and he is a farmer's son. And obviously he's sort of 50, 60 years ago, the use of chemicals on farms was kind of, oh, let's just use this one for dipping sheep, or let's just use this one for cleaning cows or something, and so there was a kind of lots of chemicals being used that perhaps wouldn't be used nowadays because they've been proved to have other problems. But don't think anyone has, apart from the Roundup one, no one's kind of got a direct link between any of them and Parkinson's. But you do wonder about the cocktail mix of chemicals that farmers use. And I don't know whether farmers are more prone to Parkinson's disease, but as I say, my family experience is that farmers have more Parkinson's disease. Okay.
I think I did nursing, started since 1969. And there were days when they started chemotherapy and we did chemotherapy. I mean, advances come and they have different ways of doing it. But I started wondering how many chemicals did we expose ourselves to? Because I have no family members that have it. And I can trace back as far as I can remember talking to family members. And then in 2019, I was diagnosed with it. And so, I was just wondering.
No, it's very interesting. And there is definitely, there are definitely links to environmental factors. But so
Yeah.
I've mentioned two that have been proven, but I think that they're, especially if you're looking 50, 60 years ago, was available in the chemical mix was definitely not what people are using nowadays, because a lot of them have been proved to be too dangerous for one reason or another. But a lot of those dangers, are increased risk factors for Parkinson's disease, is what I would say.
Thank you so much.
Okay, right. So we go to the last section about, whether then people should undergo genetic testing. Is it of any use in Parkinson's disease? Okay.
So
Thank you, Jan. Do you know how long that section will be? Because we're about at that 2:30 time or so.
Okay,
Do you know how long?
It's another 15 minutes. Do you want to lead that?
If we could watch a couple of any highlights you have from it. I know you said you had maybe some talking points on it, but maybe some of the more major sections. But yeah, the majority of the video, is okay, but I just wanted
Let-
to let
Let's
you
just
know
let it
that
run
as
and you
well.
just tell me when to stop. And if I think he's going on a bit, I'll stop
The
it.
last part of my talk will
Okay, thank
address the
you.
question, should anyone undergo genetic testing for Parkinson's based on all that? And I want to list the pros and cons for this important question. We'll start with the factors that would argue in favor of undergoing genetic testing. If you have the disease, it's certainly a very common thing that patients have a strong desire to find out, why do I have this disease, right? I mean, I'm sure everybody can relate to that. So you want to clarify the cause of the disease. And if genetic testing comes back positive and you say, okay, it's the gene XYZ, there's a variant in there, a mutation, and that's why you have the disease, that certainly then kind of in a way puts somebody's mind at ease, that there were not any other, I don't know, toxic exposures or other environmental factors maybe, or at least not didn't play such a big role. So it gives some closure there on why did the disease occur in the first place. It will allow participation in certain studies that are only offered to people with a certain mutation, like for LAG2, for example, which is not such a rare thing, especially, like I said, in Ashkenazi Jews, for example, there are studies that one is only eligible for if you have a mutation in that gene. So, if you're interested in participating in certain types of studies, you would have to get tested first to even know if you're eligible for the study or not. In the future, most experts, including me, agree that we are moving closer and closer to gene-specific targeted therapies. For example, if we at some point figure out why LAG2 causes disease and how it does that, it's quite easy to imagine that there would be a specific therapy that will only work in patients who have that underlying mutation, and that would not work in people who do not have a normal, in people who have a normally functioning LAG2. So there will most likely be gene-specific forms of therapy in the future. And in order to qualify for that kind of therapy, you would have to know what your genetic status is. And then family planning. So if you know that you have that you carry a certain mutation, then a physician or genetic counselor can tell you what the risk is for your children to also inherit this disease and be at risk for this disease. And people would often argue that will be an important aspect of why they want to know what if there is a genetic mutation in the family or not. Of course, whether the 50% chance of having a baby that then another 50, 60, 70 years later may develop Parkinson's disease, whether that will really convince anybody not to have children, that's a very personal decision, and I'm not going to discuss it any further here. But certainly many people feel that it will have an influence on their family planning if they have that information available. So those are all factors that people would say are in favor of genetic testing. In terms of negative arguments against testing, to this day, we don't have any gene-specific therapy. So what I said here is really a future prospect and hope. But right now, we're not there. So even if you find out that you have a certain mutation, your treatment for Parkinson's is going to be absolutely identical. There will be no change in treatment so far, whether you have a genetic form of the disease or not. There is certainly a factor to be considered, which is burden of knowledge or burden of anticipation for family members mostly. So if you know that you have a genetic form of the disease, all of a sudden your children will not just have a slightly increased risk like every first-degree relative of somebody with Parkinson's, but may have a much higher risk, maybe a 50% risk of also developing Parkinson's disease later down the line. And they might then feel like, well, now I should actually get tested too to know that. And that alone, of course, is a very controversial issue, because testing in somebody who doesn't even have signs of the disease yet is, as you can imagine, somewhat problematic, because then if that test comes back positive, then somebody who's completely healthy right now has to live with that knowledge that they're basically just, could consider themselves like a ticking time bomb, to use a word that many of my patients have used in the past, and that the disease will come out at any time. And that can be quite burdensome, obviously, to live with that, even though some people would say, well, I would rather know and then plan for it rather than not know, maybe for certain financial decisions. But at the same time, as I said earlier, you may actually never develop the disease, even if you have one of these mutations. So to have that knowledge can be burdensome. And then often the results are not as clear-cut as you would hope. There can be inconclusive results or variants of unknown significance. So that can make it difficult to interpret the results. The cost is certainly a factor. Many insurances do not see why they should cover the cost for genetic testing. So then you might be stuck with a cost, and you certainly want to clarify that before you get the testing. And then finally, even if the results are not truly inconclusive, they may be somewhat challenging to interpret, and certainly you need somebody who's very knowledgeable in that field. And this is particularly true if you just send a sample to a commercial entity like 23andMe, where you send your saliva sample and they send you, a certain amount of time later, they send you all the results, and then you might get this long kind of laundry list of genetic variants and results, and it may be quite challenging for you to understand, well, what does that really mean now, and what does it mean for my children and grandchildren, etc. Right? So this can be disconcerting and challenging for people.
I think that's probably a good place to end, since we're past our time. I don't know if you think so. At least you've got kind of the relative for and against for genetic testing, which you can expand to not just be for Parkinson's disease, but for any disease, if you think that you need to be tested for it, whether it's a good idea or not. There's a question.
Yes, again, thank you for that video. I like the pros and the cons. I think those are some things that folks may not be thinking about. So I think that was a really good slide. Thank you so much. We have a question from Mr. Angelo. How are you?
Yes. How are you? Fine, everybody. Thank you. I noticed that you talked about Michael J. Fox, and I was familiar with him having Parkinson's, but I thought it was after he was of age and made the movie Back to the Future. That's when they came out and said he had it. But
yeah. He wasn't diagnosed with it till after the movies, but I have heard that there were people who worked with him 10, 15 years before the movies. He was a child actor on this show that was they also have developed Parkinson's. So whether there was an environmental factor that was common in their background when they were working on that show is what I'm saying. Okay.
Wow.
Sense? Yeah. Okay.
Yeah.
The thing about Parkinson's is so remember from before we talked about Parkinson's, that it is a reduction in the cells in a part of your brain called the substantia nigra that produce dopamine. Okay. Now what happens is that say my husband was diagnosed in 2018. Okay. But one of the first symptoms of Parkinson's, it's quite common, not exclusive, because Parkinson's is a many-faceted disease, but one of the first symptoms can be that you lose your sense of smell.
Really?
Okay? Yes. And my husband lost his sense of smell in 2003. So the fact that he didn't suddenly get Parkinson's in 2018 when he was diagnosed, he'd had Parkinson's for a long time, but the amount of dopamine that your substantia nigra makes is quite capable of being reduced, but still okay, up to a certain point, at which point you start displaying far more symptoms. Okay, so the typical symptom that people think of for Parkinson's disease is some kind of shaking, either of a hand or legs.
Right.
Okay, and that doesn't develop until basically you've kind of got down to, I don't know what percentage, but perhaps 20% of the dopamine producing cells in your brain compared
Wow.
to the 100% you had when you were a kid. All right, but you've been losing it gradually, but your body's coped with that until it doesn't, and it starts to develop symptoms which are shown, which is like the shaking. So I say he got diagnosed in 2018, but one of the first things that the consultant asks is, how's your sense of smell? Oh, I'd lost that back in 2003. And you
Oh,
think,
wow.
okay,
Yeah.
all right.
Okay.
So that dopamine producing cells have been reducing for 15 years before it
Wow.
actually was obviously that he had Parkinson's.
Right.
Does that
Oh,
make,
wow.
does that
Thank
make
you.
sense? It's a
Very,
very
very
slow,
informative.
very slow progressive disease until it isn't, and then you need to start taking the drugs to increase the levels of dopamine using drugs, rather because the drugs that we're taking for Parkinson's, the levodopa, carbidopa that he talks about in the slides, that's no cure. That's just producing the dopamine that your body isn't producing anymore.
Yes. So you think probably it was something, you say the environment on the set, maybe
It's a theory. Nobody's
yeah, right,
It's
right.
like one of the examples of environmental causes of Parkinson's, which has been, put out there as a possibility. As I say, we know about Roundup, we know about the chemicals at Camp Lejeune, and there will be other chemicals for sure in the history, because, as I say, we weren't as careful using chemicals back.
Right.
Oh,
Right.
DDT, wonderful, let's kill all the mosquitoes, but unfortunately it was not very
Mm,
good for us either.
right.
Okay,
Right. Yeah, okay. Thank you very much.
you're
Appreciate
welcome.
it. Very informative.
Anybody else?
Thank you, Mr. Angelo. Have a
Yep.
good day.
Yeah.
Mhm.
Okay.
So it doesn't look like we have any other questions, Jan, but I certainly learned a lot about Parkinson's, but also some other diseases. We all got a free biology lesson. And I like the way that he explained it in terms that we could understand. So I hope we all learned something new. Any last thoughts or anything that stuck out to you about today's presentation, Jan? Anything you want to share with the group? But I did put again, your email and the PFNCA email if someone's interested in attending the symposium. And then there's also the website link for it as well to learn more information.
Absolutely. Oh, I mean, I'm delighted to speak to you and I hope that, I know it was a bit biology to start with, but I think, there are other genetic diseases which we all have heard of, like someone mentioned straight away, the sickle cell one, and there are lots of others too, which are, of interest. And so you're just knowing something more about, the risk factors to do with genetic diseases is quite a useful one, I think. So thank you for your attention, and we appreciate it.
Well, again, thank you so much, Jan, for coming on. All the participants, let's make sure to stay on to complete a poll to let us know how you felt about today's session. But we look forward to your next presentation in August. Hopefully we get to see Jared as well. Okay. But let's all thank Jan for hosting today's wonderful session. Have a great rest of your day, Jan.
Thank you, Jan.
Thank you,
Jan.
Thank you, Jane.
Thank you.
Thank you, Jane.
Bye, everybody.
Thank you.
Bye.
Bye-bye.
Have a good
Have
day.
a wonderful good day.
Thank you, Jan. And
Thank
again,
you,
thank you all
Jan.
so much for coming on to our session today. I really, really appreciate it. I'm going to go ahead and start our poll. So that way, again, you can let us know how you felt about today's presentation. So I just launched it in Zoom. So let's make sure we're all in the Zoom app. And there are 4 questions as usual. What percentage of the information was new to you? 10, 50, 75%. Would you like to learn more about this topic? Yes or no? Please rate the speaker's presentation skills, 1 being the lowest and 5 being the highest. And then how likely would you recommend this presentation to a friend or family member? Very likely, likely, or unlikely. Again, there are 4 questions. Once you hit submit poll, you're free to go. Thank you so much for attending our session with the Parkinson's Foundation. We will be hearing from them again in a couple of months, so I look forward to that. Tomorrow we have our module at 1:30 p.m. Module 5. We'll be learning more about the control center and how to maneuver and copy and paste text and photos on your iPad. On Thursday, we'll have Jordan Johnson from DC Public Library come on and talk about social wellness. On Friday, we have our advanced session on apps for Mother's Day at 10 a.m. We have our trip to Ecuador at 12 with Lou, and we'll be ending our week with Module 6, all about Zoom. So what you can do when you're in a Zoom meeting and how to add a Zoom background. Okay, but again, once you complete the poll, you're free to go. I'll see you tomorrow at 1:30. And again, thank you all so much for completing the poll. We're about 70% of the way there. Thank you. So again, make sure you scroll and find the other questions and you'll be able to hit submit poll once you submit that. But again, once you do, you're free to go. And I hope you all have a wonderful day. Thank you. We're at about 80%. I appreciate that. I'm gonna give about a minute or so. And again, thank you all so much for coming on to our session today. Tomorrow's the module, Thursday is DC Public Library, and Friday is our full fun day with our advanced training, lunch club, and module. Okay, thank you so much. Really appreciate that. I'm going to go ahead and end our poll. And thank you, thank you, thank you. Second. And there you go. Again, thank you all so much for attending our session with the Parkinson's Foundation today. I will see you all at 1:30 p.m. tomorrow. And thank you so much for coming on. Have a great day.
Hey, thanks for that.
Thank you, Alex.
Hey,
And you have a
appreciate
great
you,
one
man.
too.
You've done it again, brother. You've done it
No
again.
problem. Thank you so
All right.
much.
Take
Later,
care.
Have a
y'all.
great rest of your day,
Okay.
everybody.
Thank
Everybody,
you.
See you all
Bye.
tomorrow.
be safe,
Bye.
everybody. God
Bye.
bless.
Be safe, everyone. See you tomorrow.
Bye-bye. See you tomorrow.
Have a blessed day, gang. Have a blessed day.
See you all soon.